Hi there. Welcome back, everyone. Software analysis and design. Today, we're talking about component diagrams. So, just wanted to let you know, you are loved, you're amazing, you're strong. Yes, you can sing. You do matter. You're valuable. You're also smart, beautiful. You belong. You aren't broken. You're wonderful. You're not a failure. You're never too far gone. And you can do this all. You're awesome. And I believe in you. Let's get started. So we're going to look at component level design, and then we'll look at component diagrams and how to draw them, what the notation for them is. We'll look at a bunch of examples, and then I have an exercise for you. Surprise. So with that, what's component level design? It is a complete set of software components as defined during architectural design, but the internal data structure and processing details of each component are not represented at a level of abstraction that's close to code. Component level design defines the data structures, algorithms, interface characteristics, and communication mechanisms allocated to each software component. And why does that matter? You have to be able to determine whether the software will work before you actually build it during specification. The component level design represents the software in a way that allows you to review the details of the design for correctness and consistency with other design representations. And the work product is the design for each component represented in a graphical or tabular or text-based notation. And the primary work product is that during component level design. So we're going to focus on the diagrams because we've been modeling all semester, so we'll stick with that. But there would be other representations that are possible. According to the OMG Object Modeling Group, Unified Modeling Language Specification, the component is defined as a modular, deployable, and replaceable part of a system that encapsulates implementation and exposes a set of interfaces. Yay. In the object-oriented view, a component contains a set of collaborating classes. And in a conventional view, a component contains processing logic, the internal data structures that are required to implement the processing logic, and an interface that enables the component to be invoked and data to be passed on to it. So here we have an object-oriented component. We have an analysis class, we have a design component, and then we have an elaborated design class. So, all those go hand in hand. So we started with the class model. You already made that a few weeks ago, the print job here. And the print job in the analysis class has a number of pages, number of sides, paper type, magnification, production features. And then it has the methods of compute job cost and pass job to printer. A couple of you asked me back then, why do we need the methods already? Do we need the methods already? So it makes sense to have the methods already, and yes, they will have to be expanded some more because you still couldn't see all the white box methods. You just knew what you needed definitely for the interface, but maybe more. So now, as we develop that design component print job, we know that we have as interfacing methods compute job and initiate job. And as part of the design elaboration, all interfaces that enable the classes to communicate and collaborate with other design classes must also be defined. So we'll recall that analysis modeling and design modeling are both iterative actions. So elaborating the original analysis class may require additional analysis steps, which are then followed with design modeling steps to represent the elaborated design class. So when you look at the elaborated design class in more detail, all of a sudden that print job has a ton more attributes and also quite a few more methods. And then it has those two explicit interfaces for compute job and for initiate job. And for both of those, you have a set of methods that can be called on that interface. In a conventional component, which is also called a module, that is something that resides within the software architecture, and it usually serves one of those three important roles. It can be a control component, it can be a problem domain component, or it can be an infrastructure component. And it's derived from data flow diagrams. That's one of the ways. Data flow diagrams as well as from class diagrams. So you have your design component compute page cost on top, and then elaborate that in a module that has more details, and then an additional explanation for that method at the very bottom with a bunch of parameters that I'm not going to go through in detail. But feel free to pause here and look through the specific attributes in detail. What are we going to need for identifying the right modules, for the right components? We're going to look back at our basic design principles that we talked about a week ago. So the open-closed principle. A module or component should be open for extension, but closed for modification. Remember, we're trying to keep things local. So we don't want to mess around with what's inside the component already, but we always want to be able to build on top of that component. Then there's the Liskov substitution principle, LSP. Note that all the design principles on the slide have TLAs, 3-letter abbreviations. Apparently, that's really important to impress people. So if you want to go impress people, please learn all those TLAs. For me, don't. You can always look them up. So subclasses should be substitutable for their base classes. That means that you're always able, when you have a subclass that expands on an existing module, that you can still use that for the interface, that will still do the job. It can, in addition, do other things, but it will definitely fulfill the basic job. Dependency inversion principle. So you want to depend on abstractions, not on concretions, which means if you implement an abstract interface, you want to make sure you can depend on that and don't have to know about further details that have been implemented. Interface segregation principle. Many client-specific interfaces are better than one general purpose interface. So if you have different types of clients, then it makes sense to have several interfaces for those. Release reuse equivalency principle. So the granule of reuse is the granule of release. This rule is close to a tongue twister. But what it means is it makes sense to have your releases related to the reuse. So when you have reused something, then you make an additional release. When you have a new release, and make sure you optimize your reuse with it. Common closure principle. Classes that change together belong together, which means that within a package, you want to have kind of the same release cycle frequency. Or change frequency, better than release frequency in this case. So let's say in our print job, there are several classes in there, and when print job needs to get modified, all the other classes in print job should probably get modified along with that. If not, why would they be hanging out in the same module? And then there's the common reuse principle. Classes that aren't reused together should not be grouped together. So if they are not close enough, if there is no cohesion in the module, then they shouldn't be hanging out in the same module. For the component level design, there should be some naming conventions established for the components specified as part of the architectural model and then refined and elaborated as part of the component level model. I will tell you that the assignment that we'll be doing for this is more limited, so we don't have big naming conventions there, but think about it. How can you make, how can you make sure that they are named according to a convention that makes sense and that makes clear when things belong to the same module and the same packages? Interfaces provide important information about the communication and collaboration, as well as helping us to achieve the OPC. There was the TLA. Which one was OPC? Open close principle, OCP. Oh, looks like there might be a typo in there. Oops. Dependencies and inheritance. It is a good idea to model dependencies from left to right and inheritance from the bottom, derived classes, to the top, the base classes. Second to last, cohesion. The conventional view is the single-mindedness of a module. So one module has one purpose. And in object orientation, that's a little more detailed. It implies that a component or class encapsulates only attributes and operations that are closely related to one another and to the class or component itself. So same idea, but in a few more words and a little bit more specific. There can be several levels of cohesion. There can be functional cohesion, layer cohesion, communicational, sequential, procedural, temporal, and utility. So cohesion is something that you will come across over and over again in your software engineering career. And then last, coupling. So in the conventional view, this is the degree to which a component is connected to other components and to the external world. In the object-oriented view, it's a qualitative measure of the degree to which classes are connected to one another. And the level of coupling can also be in very different ways, from content to common to control and so on, to inclusion or to external. Now, let's get into the modeling part. We are back to the structural models, and today we are with the component diagrams. So let's take a look at a component diagram. We see the component in the big blue box, and then we have provided interfaces on the left, which are denoted by those bubbles, and then there are ports denoted by small little squares, and then we have required interfaces denoted by the open side that can then embrace a provided interface. What does that mean? A component diagram breaks down the actual system and the development into various high levels of functionality. Each component is thereby responsible for one clear aim within the entire system and only interacts with other essential elements on a need-to-know basis. So only need to know, which means high coupling, low cohesion, low coupling, high cohesion. Yes, low coupling, high cohesion. So low coupling means we only interact with the essential elements on a need-to-know basis, not beyond that needed interface. So this example here shows the internal components of a larger component. The data, the account and inspection ID, flow into the component via the port on the right-hand side and are converted into a format that the internal components can use. So we read this diagram starting from the right. The interfaces on the right are known as the required interfaces, which represents the services the component needed in order to carry out its duty. The data then passes to and through several other components via various connections before it is output at the ports on the left. Those interfaces on the left are known as provided interfaces, so the stuff that the component provides, which represents the services to deliver by the exhibiting component. It's important to note that the internal components are surrounded by a large blue box, which can be the overall system itself, in which case there would not be a component symbol in the top right corner, or it could be a subsystem or component of the overall system. In this case, the box is a component itself. So in this case, the whole big blue box is also a component, a subsystem. Basic concepts are given here. So a component represents a modular part of a system that encapsulates its contents and whose manifestation is replaceable within its environment. In UML2, a component is drawn as a rectangle with optional compartments that are stacked vertically. A high-level abstracted view of a component in UML2 can be modeled as a rectangle with the component's name to the left, a rectangle with the component icon in the middle, or a rectangle with the stereotype text and or icon, as you can see on the right. All of these are valid. You know, I like it when stuff is explicit, so I'd go for the rightmost option. Interface. In the example below, you see two types of component interfaces. The provided interfaces, that's a symbol with a complete circle at their end and represents an interface that the component provides. It's often called a lollipop. The lollipop symbol is shorthand for realization relationship of an interface classifier. And then the required interface symbols with only half a circle at their end, it's also known as a socket, and it represents an interface that the component requires. In both cases, the interface name is placed near the interface symbol itself. And then using an interface, just an example for this one is an order system. So we have the component order system, and then we have a required interface to customer lookup, and a repository provides that customer lookup interface. And then we also require a product accessor interface, and the inventory system provides that product accessor interface. And then we have subsystems. So the subsystem classifier is a specialized version of a component classifier. And because of this, the subsystem notation element inherits all the same rules as the component notation element. The only difference is that a subsystem notation element has the keyword of subsystem instead of component. Ports are represented using a square along the edge of the system or a component. A port is then often used to help expose required and provided interfaces of a component. So you see that the port is denoted by the red arrow, or pointed to by the red arrow, this little blue square. And here we see the different types of relationships that are possible. So graphically, a component diagram is a collection of vertices and arcs, and it commonly contains components, interfaces and dependencies, aggregation, constraints, generalization, association, and realization relationships. It can also contain some nodes. So here we see the association, a semantic relationship that can occur between typed instances, and it has at least two ends represented by properties, each of which is connected to the type of the end. More than one end of the association may have the same type. For composition, composite aggregation is a strong form of aggregation that requires a part instance be included in at most one composite at a time. If a composite is deleted, all of its parts are normally deleted with it. And for aggregation, a kind of aggregation that has one of its end marked shared as kind of aggregation means that it has a shared aggregation. And then we have the constraint, a condition or restriction expressed in natural language text or in a machine readable language for the purpose of declaring some of the semantics of an element. And then dependencies. A dependency is a relationship that signifies that a single or set of model elements requires other model elements for their specification or implementation. That also means that the complete semantics of the depending elements is either semantically or structurally dependent on the definition of the supplier elements. Finally, links. A generalization is a taxonomic relationship between a more general classifier and a more specific classifier. And then each instance of the specific classifier is also an indirect instance of the general classifier. Thus, the specific classifier inherits the features of the more general classifier. So you know generalization from object-oriented programming, same story as in the class diagrams. So when do I use them and how do I make them? That was the notation. When I use them. Use component diagrams when you're dividing your system into components and when you want to show the relationships through interfaces. The breakdown of components into a lower level structure, that's what gets represented. How do you make them? So first you decide on the purpose of the diagram. So what exactly is it that you want to show? Do you need the actors in there? Do you not need the actors in there? You'll see that a little further down. We have examples for both. And then add components to the diagram, grouping them within other components if appropriate, like we saw with the systems and the subsystems and the subcomponents within them. And then add other elements to the diagram, such like classes, objects, and interfaces. And then add the dependencies between the elements of these diagrams. So here's a ticket selling system component diagram example. So the ticket seller component sequentializes requests from both ticket selling systems and clerks. The component has, it can process credit card charges, and the database contains the ticket information. So you see the actors in this picture, they're present, the outer actors, and then we see dependencies from actors to components. We see the required and provided interfaces, and with that, we have a pretty good overview of the architecture of the system. And then, order processing system. So one main benefit of component diagrams is to simplify the high-level view of the system. And the figure below is a much larger view of what is involved in an online store. By using a component diagram, we can see that the system is a group of nearly independent components or subsystems that then interact with each other in a specifically defined way. Each component here is responsible for the action for which it is named and interfaces it provides. And as long as those requirements are maintained, changes to one component will not percolate to other components. Remember that we said we want the changes to be local. So if I have my system structured like here, my order processing system, then it doesn't matter if I change something in the storefront, if I make that look different, because the interface to the storefront will still be the same. It doesn't matter if I change my shipping from FedEx to UPS or the other way around, or to another third-party provider, or if it's all done by PostNord, it will only be handled within shipping. And the interface to order processor will remain exactly the same, so it doesn't matter. That way, my changes are local, and the effort that it requires to make those changes will be limited. This is where we often get in trouble with the evolution of software systems, that the changes drag across the system and therefore cost more and take longer than we initially budget for it. Here is a nested component structure for a store component. So to show that nested component structure, we just draw the component larger than normal and then place the inner parts inside the name compartment of the encompassing component. So the figure above here shows the store component nested structure. Inside store, we have orders, products, and customers. And then we have external interfaces that are required, that are account and order entry. We can also use component diagrams to model source code. So we can use them either in forward or reverse engineering. And we can then identify the set of source code files of interest and model them as components stereotyped as files. For larger systems, we can use packages to show groups of source code files. And we can consider exposing a tag value indicating such information, like the version number of the source code file. We can denote the author with it, and we can also check the date it was last changed or tag that value. And there are tools that we can use to manage the value of those tags. We can model the compilation dependencies among those files using dependencies. And again, tools can help to generate and manage these dependencies. I just want to show you a couple of options for this. This is not the focus of the course, but I want to show you that, yes, there is a whole lot more you can do with component diagrams that you may not have thought of before. So for Java source code here, for example, there are a couple of components around an item that is connected to loan, that is connected to borrow information, that is connected to reservation, and that is connected to title. So all of this is going in a happy circle. There is a circular dependency that I'm not sure of whether that's great. Maybe that is exactly why we needed the component diagram to figure that out. Because if we re-engineer source code into models like this and find out about those circular dependencies, when we then re-engineer the code and say, you know what, circular dependency, that sounds like trouble, then we can develop a better structure for the system. And then one diagram example for C++ code, this one includes some versioning. So we see no gnarly circular dependencies on this one. What we do have is just different versions. So while inter-P, IRQ, and device are still apparently in version 1, all the other ones have higher versions, and especially Signal has been developed quite a bit further. So that helps us understand how quickly parts of our system evolve. Modeling an executable release is also possible. So we can model our DLLs. We identify the set of components that we'd like to model, and then typically that will involve some or all the components that live on one node, or the distribution of these sets of components across all nodes in the system. And then consider the stereotype of each component in that set. For most systems, we'll find a small number of different kinds of components like executables, libraries, tables, files, documents. And then you can use the UML's extensibility mechanisms to provide visual cues or clues for these stereotypes. And for each component in the set, consider its relationship to its neighbors. So most often, this will involve interfaces that are exported or realized by certain components and then imported or used by others. If you want to expose the seams in your system, model these interfaces explicitly. That's going to help make it more transparent. And if you want your model at a higher level of abstraction, then you light these relationships by showing only dependencies amongst the components. Almost done. Last one on this. Modeling a physical database. We start with identifying the classes in your model that represent your logical database schema. And then you select a strategy for mapping these classes to tables. You will also want to consider the physical distribution of your databases. And your mapping strategy will be affected by the location in which you want your data to live on your deployed system. And then to visualize, specify, construct, and document your mapping, create a component diagram that contains components stereotyped as tables. And where possible, use tools to help you transform your logical design into a physical design. So with that, at the bottom, we have our school database, and the school database is composed, it's a composition, by courses, departments, instructors, schools, and students. Wonderful. Take a deep breath. With that, a couple more examples here. Here is a component diagram for a library management system. So library systems were some of the first systems in the world to become widely run by computers. Today, many of these systems are managed in the cloud by third-party services rather than internally. And though the term library system typically calls to mind a way to monitor printed books, library systems today organize all kinds of data checked in and checked out by users, not just books. The transactions create a network of relationships between the components of the library system. And to understand how these relationships work and how the system functions overall, take a look at this UML diagram. You can even end up using something like this as a template. This is from Lucidchart. So if you are interested, Lucidchart is one of the UML tools that you can use. I believe they have a community edition. Also, note that the notation looks ever so slightly different because this is actually a UML 1.x. Do you note the biggest difference? Yes, it's the component symbol that looks slightly different. So you have those two bars on the left. And in UML 2.x or in UML 2, you have these two little bars in the top right-hand corner of the component. So it's a little bit more subtle. And then component diagram for an ATM system, because, you know, almost every modeling lecture has to have a classical example of an ATM system in there. So here we go. Here's ours for the day. A component diagram is similar. Oh, did you wonder why? So ATM systems are so readily used as examples because they're fairly simple. They have an embedded part and they have a human computer interaction or a user interface part. So that's what makes them the perfect example for classrooms. A component diagram is similar to a class diagram in the sense that it illustrates how items in a given system relate to each other, but component diagrams show more complex and varied connections than most class diagrams can. And in this diagram, each component is enclosed in a small box, and the dotted lines with arrows show how some components are dependent on others. For example, you have the card reader, the web page, and the client desktop, and the ATM system, and they're all dependent on the bank database. The dotted lines with circles at the ends, also again known as lollipops, indicate a realization relationship. Again, this is also UML 1.0, 1.x. Another example from our friends at agilemodeling.com, the seminar registration system that we've looked at a few times. So here we have the components for seminar management, for student administration, and then we have the facilities that we depend on, the students, the seminars, and the schedule. We depend on all of these. And then we have a security component and a persistence component that all of these other components depend on. This one is again UML2 because you see how those icons are in the top right corner of your components. And then a slightly more complex one, just so you know that not all component diagrams are going to be that simple. This one is an insurance policy administration system. And it might be hard to read on your screen. So either download the slides as PDF or check for wikipedia.org, the component diagram in there. That's where I got this example from. And then you can blow it up and make it larger. So we have this large subsystem that is the application components of the policy administration. And then we have some more external components, and you see that a couple of them are denoted as COTS, that's short for component off the shelf. So for example, the infrastructure component rules engine on the right-hand side, and the infrastructure component document management at the bottom, and then also the infrastructure component identity management at the bottom right. All of those are external components off the shelf. That means those have been developed by somebody else, by a third party, and I can buy them. Or we have developed them as a standard product, and then we do some other customer development that we then sell separately. And then within the policy admin subsystem, we have several application components. So we have the underwriting and rating engine, we have the UI generator, and then we have the forms management in the bottom left. And then we have two web services, the product server and the policy server. And we have two thin clients, the policy admin UI and the product admin UI. And then we have a ton of interfaces in between all of those. And we have a couple of delegates. And then we have a couple of ports from the outside. So it can get pretty complex fairly soon with all those interfaces. So hit pause here and examine this in a little more detail, or rewind a little bit if you lost track of where I was telling you about the components. Good. It is your turn. Yay. So let's try this out. Your turn to make a component diagram. I'd like you to make two. Make one for the amusement park example for the entrance system that we've been working on. And then make one for the other example, for the robot example that we've been talking about. So for both of those, I would suggest to take a look back at your class diagram, take a look back at your sequence and activity diagrams, and then start writing down your components, like what are the physical components that you want to have deployed. Think about the design guidelines for how often are these parts going to change. If a part inside that module is going to change, does that mean the rest of the module is going to change or not? And then depending on that, you make the distribution of your components So everything that goes into one component changes together. Things that get updated at different rates of change, or that come from different parts of the domain, or that are a control element, those go into different modules. So take a look back at those design guidelines. And I repeated the most important ones at the beginning of this lecture, but also look back to the one in last week. And then develop your component diagrams. Let me know your questions, and I'm looking forward to hearing them either here on another platform, and enjoy the rest of your day. And make sure you model some of these component diagrams, because if you don't try them out, guess what? Lecture goes in here and goes out there. So get a piece of pen, no, a piece of paper and a pen, that thing, or open up your favorite drawing program, and then just go ahead and play around with those component diagrams for a bit. Thank you very much for tuning in, and I'll see you soon.